intermolecular forces are different than intramolecular forces. So intermolecular forces are what keeps molecules attracted to one another, whereas intramolecular forces are the actual bonds within the molecule itself. So clearly what's bonded to the molecule is way stronger, like 96% stronger than what these are your intermolecular forces. So like the reason why water puddles together is because of intermolecular forces, but the actual bonds in water are intramolecular. Get it? All right, so we're going to start with ion dipole, which is not the strongest type of bond. So we're going to kind of wrap around all of them, and at the end, I'm going to make you create a note card where you list all of the types of forces and which are the strongest, because you'll always go back to lots of multiple choice questions that'll say, which of the following has the strongest melting point or highest melting point or boiling point? And you're just going to look at whoever's the strongest type of bond will be the one that has the highest melting point. So ion dipole is not the strongest, but we're going to start with it. Ion dipole is when you have an ionic compound that interacts with a dipole. A dipole comes from a covalent compound. So this is an ionic with a covalent. So ionic compound with covalent. And it has to be a polar covalent, not just a nonpolar covalent. That's something else. So ionic with covalent. So polar molecules like water, like ammonia, those would be different molecules that would be able to interact with an ionic compound. So anytime that you have attractive forces, it's always going to be with one end being positive and the other end being negative. So you have electrostatic forces of attraction when you create intermolecular forces. That's the only way that an intermolecular force attraction occurs, is between positives and negatives. So you have to have positive and negative attraction for intermolecular forces, always. So if it's not available, perhaps there isn't a positive and a negative, like in an anion and a cation, it creates it through a dipole. We know that in water, when we have a dipole moment, you just took this test, that the electrons pull this way, and this becomes slightly positive, and this becomes slightly negative. So you create a polar end to the molecule, creating that negative end, or creating the positive end itself. We know that in ionic compounds, they are cations or anions naturally, so they have always a positive or a negative part. So this is showing you that if you have a cation here, that you could have a dipole, so some molecule that has a negative end and a positive end, arrange itself so that it's attracted to the cation. So this is your dipole. These are all your dipoles. So this is the covalent piece here that's attracted to the ionic piece here. This is an ionic piece here. This is your anion. And these are your dipoles, your covalent piece attracting to the anion in the ionic compound. Get it? So your dipole is your molecule. Your cation or anion comes from the ionic compound. That's what an ion dipole is. So for example, we have sodium chloride. And the AP exam, I've seen this twice, almost the exact same question in different years. It asks you to draw the dissociation, which dissociation means the dissolving process of sodium chloride, or it'll give you a different type of ionic compound. So how does sodium chloride dissolve in water? In fact, how does any ionic compound dissolve in water? So the way that it's going to do that is through ion-dipole interactions. And if something doesn't dissolve, it's because the ion-ion interaction is stronger than the ion-dipole interaction. So what you have to start is sodium positively charged, chlorine negatively charged, and these are together, right? There's an exchange of electrons transferred there that creates a cation and an anion. So when these go into water, I dump this into a beaker of water, there are dipoles all floating around in here. And those dipoles are willing to separate the sodium and the chlorine if they're strong enough to pull this apart. If this is too strong, then this interaction with this and this interaction with this will not break them apart. So sodium chloride comes in, and in fact it can dissolve, and so you will have to draw these representations. So sodium is surrounded by the water molecules with the orientation of oxygen facing the sodium and the two hydrogens on the outside. if you have to draw this for a quiz or test for me, and you don't put the correct arrangement, and you put your hydrogens facing your sodium, it's wrong, right? Because hydrogens can't pull apart the sodium, only the oxygen, which is slightly negatively charged, can. So it pulls it away, and the chlorine gets surrounded by all the hydrogens, which are slightly positively charged, and it pulls that away. So the forces between the ion-dipole are greater than the ion-ion interactions. Ion-ion is that, Na plus and Cl minus. That's an ion-ion interaction. So when that occurs, you have dissolving. Another word that we use, remember, is dissociation, which means it breaks it apart. So it may ask you to show the dissociation of that. Any questions? So ion dipole and Coulombs Law. Some ionic compounds do not dissolve in water. The solubility of ionic compounds can be explained through Coulombs Law. If the cation-anion attractions are stronger, then the ion-dipole attraction of the compound will not be soluble. I just wrote that for you before. So we don't necessarily say cation-anion attraction, we say the ion-ion attraction. So we're going to go through the list eventually, but right now we know that ion-ion is stronger than ion-dipole, right? Like ion-ion precedes, ionic compounds precede ion-dipoles. So sometimes it will pull them apart and sometimes it won't. So let's take a look at this example with magnesium hydroxide and barium hydroxide. So it says magnesium hydroxide is not soluble in water, but barium hydroxide is soluble in water. Just as a side note, the AP exam used to make you memorize all your solubility rules. Do you remember that from like honors chem? On the back here was all the solubility rules. Well, you no longer have to memorize those. There are a few that you have to know, which we'll start going through them. But right now, like group 1A is always soluble. Nitrates are always soluble. Those are two that we always have to remember. So I'm going to jot them down. We can start remembering them. Group 1A is soluble, and nitrates are always soluble, which is NO3 minus. That's a general rule for the AP exam. You're just going to make sure you memorize that. So would you have to know that magnesium hydroxide's not? No. They would have to tell you that. And if they told you it, then they would want you to explain why. So sometimes the exam doesn't expect you to know stuff, but they tell you something. They expect you to be able to explain the theory or the concepts behind it. So the reason why that's not soluble is because the force of attraction between magnesium and hydroxide is stronger than the force of attraction between barium and hydroxide. So how is that true? What do you think? Your periodic trends, what does that tell you? According to Coulombs Law. So Coulombs Law is charge and distance. Do they have the same charges? Yes. Barium and magnesium are in the same group, so they both are +2 charges. Hydroxide's -1. So I can't look at charge, so what am I looking at? Distance. And who's smaller? Which means that its nucleus is closer to that hydroxide covalently bonded anion, and it's going to have a greater force of attraction between magnesium and hydroxide than it would with barium hydroxide. So when the water molecule comes in, the dipole, it has a greater ability to pull apart this because this attraction to its hydroxide is not as strong. So when you look at this, it's showing you that the relative distance between your magnesium and your water molecule is much smaller, and then your barium distance is much larger. So this is true that it won't dissolve, but it's also true on the other side that magnesium has a greater attraction to water than barium does. Do you hear what I just said? I just told you before that magnesium won't dissolve in water because its force of attraction is too strong to its anion, right? But then I just said to you now that magnesium has a greater force of attraction to water than barium does. The same thing holds true. It's because of its size. So if I say, for example, I dumped this magnesium ion and barium ion into water without any other anion in there, magnesium would have a greater force of attraction to the water molecule because of its distance. But if I put it in as magnesium hydroxide, the magnesium hydroxide is sticking stronger together than the barium hydroxide. And so that would stay insoluble, and then barium hydroxide would be soluble. So it says the ion-dipole forces of attraction between magnesium and water are stronger than those between barium and water for the same reason as the previous slide. Shorter distance between negative dipole and protons, longer distance between negative dipole and protons. Ion-dipole intermolecular forces versus your ionic bonds. These are your ionic bonds. These are your ion-dipole. If ion-dipole is stronger, it pulls it apart. That's basically all it's saying. So two forces working against each other through Coulombs Law. One of the forces will be stronger than the other. And if ion-dipole is stronger, it dissolves. If ion-ion is stronger, it doesn't dissolve. Do you get that? As simple as that. So those are your justifications there. You're not just going to say ion-ion is stronger, therefore it doesn't dissolve. You would say ion-ion is stronger and then discuss force of attraction with Coulombs Law, either charge or distance, to discuss why it's not dissolving. And then this is just the justification that we just discussed about that. So magnesium hydroxide is not soluble in water, but barium hydroxide is, because for the alkaline earth metals, so that's group 2 going down, forces of attraction from ionic bonds decreases more rapidly than the ion-dipole intermolecular forces when moving down the group. What this means, basically, this blurb here, is that solubility increases moving down that group. And why is that true? Because what's happening as you move down the group? Yep, the radius is getting larger. So the cation is getting larger as you move down the group, so therefore the ion-ion interaction gets weaker. So your solubility would be increasing as you move down that group, based on atomic radii trends or cation trends. All right, our next force, intermolecular force, is dipole-dipole. Dipole-dipole is between two polar covalent molecules. So polar covalent and polar covalent. They have to be polar to begin with. And this only occurs between molecules that are covalently bonded, right? So I'm not dealing with an ion anymore. It's covalently bonded compounds. So it says the attractive forces between the negative end of one polar molecule and the positive end of another polar molecule arrange themselves so that they attract. So if I have a water molecule that's attracting to another water molecule, the oxygen gets attracted to the hydrogen on the other molecule, creating a hydrogen bond, right? We'll discuss those also. So always, intermolecular forces, I wrote this earlier, are always between the electrostatic force of attraction between a positive end and a negative end. So these positive and negative ends are created because one molecule has a greater electronegativity and is pulling the electrons towards it, and so then that atom gets slightly negative, right? So the negative end aligns with the positive end. Molecules with dipole moments experience Coulombic interactions when they're in close proximity to one another. Without intermolecular forces like dipole-dipole, nothing stays together. Everything would just exist in the gas phase, right? Because you couldn't have any molecules coming together to create liquids or solids. So you have to have intermolecular forces of attraction. This is an arrangement of dipole-dipole. So if I stuck a bunch of water molecules together, and this is what it looked like, this is obviously not water, let's pretend this is hydrochloric acid, HCl. So one end gets negative, one end becomes positive. All of the molecules arrange themselves, and you can see that the positive and negatives are attracted here, but also the positive and negatives are attracted going up and down, and you create lots of dipole-dipole interactions to create this liquid, or this puddle, or this solid. So in solid, molecules are held close together in a regular pattern by dipole-dipole forces that attempt to maximize attractions and minimize repulsions. So they're trying to arrange themselves so that they're like this and not shifted, causing a break in that. So those molecules' intermolecular forces, which we'll get to in a little while, we can sever these. We can weaken them. If it's a solid, then it's held rigid, right? But if it's a liquid, then they're kind of moving around. And when you break those intermolecular forces, then they become gases. So without intermolecular forces, you never get this kind of interaction here. Dipole-dipoles in liquids. Also attempt to maximize attractions and minimize repulsions. These forces are strong but not as strong as in the solids, so the molecules have more freedom to move. So you can see that they're still arranging themselves and keeping them together in like a puddle, but they're not broken yet. All right, so far, this is my list. I have ion-ion being strongest. I have ion-dipole being my next. And then I have dipole-dipole interactions, which we just discussed. Within dipole-dipole interactions, that's between any covalent polar molecule, we have hydrogen bonds. But hydrogen bonds are the strongest type of dipole-dipole. So this is something that students get really confused on. Hydrogen bonds are not something different. They are a dipole-dipole force of attraction, but they have a specific name called a hydrogen bond. So if I ask you to identify the force of attraction or the intermolecular force on a specific molecule, and you write it has hydrogen bonds and dipole-dipole, not bonds, I'm sorry. It has hydrogen, yeah, I guess I had to say that, hydrogen bonds and dipole-dipole interactions. I'm going to mark that off wrong because hydrogen bonds are dipole-dipole interactions. It's just a specific type of them. Do you understand that? So hydrogen bonds are a type of dipole-dipole intermolecular force. And we use the word bonds here, but really it's not a bond. You don't create an actual intramolecular bond with these hydrogen bonds. We just use the phrase hydrogen bonds because it's a very strong type of intermolecular force. So we have ion-ion, ion-dipole, dipole-dipole, but in here really comes out kind of before this, hydrogen bonds. Because we could have dipole-dipole that are not hydrogen bonds, and I'll explain that in a second. So a hydrogen bond specifically, this is important that you recognize them. They like to ask questions, multiple choice. They show you a bunch of molecules and they'll say pick which molecule has hydrogen bonding occurring. It just doesn't mean that there's a hydrogen present. So it says it occurs between a hydrogen that is covalently bonded to fluorine, oxygen, or nitrogen, and another fluorine, oxygen, or nitrogen with at least one lone pair. So it's hydrogen attached to oxygen, nitrogen, or fluorine, and then also that hydrogen has to be attracted then to a lone pair on an oxygen, nitrogen, or fluorine. So here's hydrogen attached to, this is oxygen, nitrogen, or fluorine, which is going to probably be bonded to a carbon. And then this hydrogen is attracted to the lone pair on this, which is an oxygen, nitrogen, or fluorine. Following? 5 to 10 times stronger than any other dipole-dipole attraction. So if you have H bonds, that's the strongest type of dipole-dipole that's present. So why are hydrogen bonds so strong? So fluorine to hydrogen, oxygen to hydrogen, and nitrogen to hydrogen bonds are extremely polar. So if I'm going to draw these out, like an FH molecule, strong pull of electrons over here, 1, 2, 3, 4, 5, 6 there, we're going to say. All these electrons in this bond are held super tight there. So most of my negative charge gets pulled to this end, right? Same thing that's true for oxygen and nitrogen. Out of those, which one is most electronegative, by the way? Which one's going to be the most polar bond? Yeah, fluorine. Why? It's the most electronegative. Why is it the most electronegative? Because it's the smallest atom, right? So its nucleus can pull the electrons that are held in that bond much closer to itself. Agreed? So I get a highly negative end to this molecule, or to this bond. The atoms are very small. Nitrogen, oxygen, and fluorine are really small. So the partial charges caused by the differences in electronegativity are highly concentrated, which is why I'm drawing this so large over here. So the electrons are spending most of their time on this side of the bond. The lone pairs then, on the other piece, on fluorine, oxygen, and nitrogen increase the already partially negative charge on these atoms, thereby creating a stronger attraction for the slightly positive hydrogen. So here's what happens. I have this occurring, and then I have on another, say, fluorine over here, 1, 2, 3, 4, 5, 6, that's bonded to something else. we have these lone pairs here. Then this becomes slightly positively charged, but more so because most of the density is being pushed towards this other side, right? So this is slightly positive over here, and then these are very negative over here because of these lone pairs. So then you get a strong force of attraction between them. So it's because of the strong electronegativity on nitrogen, oxygen, or fluorine that makes both sides of this, the hydrogen end very positive, and then the lone pair end very negative. So here's hydrogen bonding between water molecules. So on this slide, I want you to draw your arrows and your slightly negatives and your slightly positives. All right, so you should have drawn that this becomes this way and this goes this way. Slightly negative, both of these are slightly positive. Again here, creates negatives, positives. And so you'll see right from that negative, positive right here is where you have your hydrogen bonding occurring. What is not a hydrogen bond is this to this. Do you understand that? That's an intramolecular bond. Hydrogen bonds are this attractive force here. Do you get some attractive forces here? Probably. You could end up with that. If I draw another water molecule, it's going to arrange itself in this direction with a slightly negative on that end. Agreed? Does it have to be water? It could be any molecule that has the lone pair. So I could have water being attracted to another molecule and still creating hydrogen bonds to it. Does that make sense? So we're just going to get through hydrogen bonds today, and then I'll stop. So both form hydrogen bonds. I just drew this for you. This is showing you hydrogen bonds between water and methanol. So methanol is this structure here. It has three hydrogens around this carbon and an OH. So this is what makes it an alcohol. Alcohols all have OHs attached somewhere in their structure. So you could have like isopropyl alcohol, ethanol, methanol. All the alls tell you that it's an OH. Do you understand that? Write that down somewhere. Because that comes up on the exam often, and it's just an expectation that you understand that anything with an OL means an alcohol. So methanol has that OH bond there. So water, being slightly positive on this end, slightly negative on this end, can also be attracted to methanol, which means that when you mix these two liquids, they dissolve, right? They dissociate, they kind of mix with one another. So that's called miscibility. We'll get to that too. So something that's miscible versus something that's immiscible means that it mixes completely. So like if you, as you get older, and perhaps you attend a bar at some point, sometimes they water down their alcohol because you can't tell, it's just mixed, right? Water mixes with any type of alcohol because of hydrogen bonding. So you'll see no difference in it at all, just they're saving money. All right, hydrogen bonds with acetamide. So acetamide here, we don't see water, do we? Can you recognize hydrogen bonding if you were just given both of these? So for yourself, I want you to really examine this and determine why is there a hydrogen bond present. So what are you looking for? First thing, hydrogen. And what are you looking for hydrogen to be attached to? Not lone pairs. N, F, or O. That's the first thing it has to be attached to is an N, F, or O. Because you can have hydrogen attached to a carbon, but that's not going to have hydrogen bonding because the carbon's not going to make that hydrogen slightly positive enough. So it has to be hydrogen attached to an N, F, or O. And it is here. And then this hydrogen then, because it becomes so strongly positively charged, is attracted to the lone pair on an oxygen, nitrogen, or fluorine, which makes that negatively charged. And then on this end, again, I have hydrogen attached to an oxygen, nitrogen, or fluorine, which makes that positively charged. And again, a lone pair here makes that negatively charged. I just want to point out to you that I can have a structure like this, CH4. This cannot create hydrogen bonds. Because no matter what, the pull on this, for this hydrogen is never going to become positive enough to be attracted to a lone pair of electrons here. It will gain something, but the overall molecule is not polar, right? So we're not going to end up with any hydrogen bonding forces of attraction there. So in this molecule with acetamide, we end up with 2 hydrogen bonds in this molecule, which makes this even stronger. So the boiling point here is 221 degrees Celsius. What's the boiling point of water? 100. Why do you think this has a higher boiling point? They're what? Well, the hydrogen bonds are stronger in general, but why is acetamide, yep, has more hydrogen bonds? So when water hydrogen bonds to itself versus acetamide hydrogen bonding to itself, it has more, it can bond twice to itself, plus all the other molecules that are surrounding it. So the more hydrogen bonding there is in a molecule, the higher the boiling point will be. We'll get to those too. Ethanol. Is this an alcohol? Why? It doesn't end in OL, so it's not an alcohol. It's ethanol. It does not form hydrogen bonds. Hydrogen is bonded to carbon. In this example, it's bonded to carbon, so it's not bonded to nitrogen, oxygen, or fluorine, so it's not going to form a hydrogen bond. I do end up with lone pair electrons here, so if another one comes in, like this, I will possibly end up with some forces of attraction, and I'll explain that later, but you're not ending up with a hydrogen bond. You cannot call that an H bond, this attraction to this, okay? So that's not going to happen. So let's look at this slide. It says hydrogen bonds with their boiling point, and it shows you their period. So just take a moment to look at this, and then I'll explain it to you. Okay. So what do you notice? What is the x-axis telling you? Yes? Your period, and as you're going across your period, right? Periods go across. So as I go across my period, look, you hit carbon, nitrogen, and oxygen. They're all bonded with hydrogen. This is hydrogen bonds, right? So I'm bonded with hydrogen. You'll see that the highest boiling point is water here. Does NH3 have hydrogen bonds? How do you know? You're just going to guess? I wouldn't. I wouldn't guess. I would draw it. I would draw NH3 out. And I'd say, oh, hydrogen's bonded to a nitrogen, oxygen, or fluorine. And then another nitrogen, oxygen, or fluorine will come in. And here's the lone pair on that nitrogen. So then I'm going to create hydrogen bonding here, right? So this, though, is not as strong as a hydrogen bond as water. Why do you think? This was on your test. Yeah, something about the lone pairs. Yeah? Has a greater dipole moment because it's more polar, which is why polarity from last chapter is so important. So water has a greater dipole moment, so therefore it has a higher boiling point because those water molecules can create stronger hydrogen bonds. As you're going across period 3, look, silicon, phosphorus, and then sulfur. So increasing boiling point there. Why do you think that's true? Yep. More polar. Geometry plays a role with this too. So if something is not polar, you're going to have low boiling point. You can't have strong forces of attraction, dipole-dipole interactions. Same thing as you're going across here. So polarity increases going from left to right across the periodic table as a general trend. We know because the size of those atoms is getting smaller, there's more pull between those bonds. So you have, as a general trend, going across the periodic table, as electronegativity increases, you create more polar dipole moments. A stronger dipole moment means higher boiling point. We'll stop here, and we're going to start looking at some of the problems. All right, so we left off yesterday with that graph where we talked about which compounds here, which molecules had the greatest boiling points. So what was the main reason? Well, these two had the most because they had hydrogen bonds, but why did we see an increasing trend as we go across a period? So what happens as you're going across? Greater electronegativity makes that molecule more polar, and the more polar something is, the greater the dipole moment is, and the greater that attractive force you have between your pluses and your minus ends, right? That's what you got to focus on, is the greater the pull on a molecule, the greater the electrostatic force of attraction there would be between a positive end and a negative end. So if one end gets really positive, then the other end is really negative, then you're going to have a greater force of attraction. So that happens as you have greater electronegativity. There's a greater pull on that tug of war. The other thing that happens as you go across this is that these molecules, the atoms within them, are getting larger, just because there's more electrons in there. I'm going to talk to you today a little bit about something called polarizability. So where we're at right now is looking at potential energy. Do you remember this slide? That was from last section, right? So that had to do with chemical bonding. And remember, I was here and I said my bonds are far away. So what does that mean, high or low? High potential energy. So when things are far away, it's like the rock on the top of the hill. It has a lot of potential energy to go down that hill. So when atoms or molecules, in this case, are really far away from one another, they have high potential energy. And then as they come closer and closer and closer, we have low potential energy. So the potential energy of the electrons that are associated with the negative pole of a molecule decrease as they approach the positive pole of another molecule. So assume we have two molecules. They both have polarity, dipole moments. So this molecule is approaching this molecule. They have high potential energy to come together and have attractive forces. So you just need to recognize that potential energy decreases as they come close together. So if this is a water molecule coming close together, the attractive ends of the positive and the negative ends create a low potential energy system. Simple enough. High when you're far away, low when you're close together. So molecules with stronger dipoles have stronger attractions for one another. I just explained that before. The greater the negative end, the greater the positive end, they stick together more. The potential energy decreases as the molecules move close together, and then energy must be added in order to weaken or break in these intermolecular forces. So potential energy increases as the molecules move away from one another. This is a key word here. Weaken or break. So when I have a solid going to a liquid, I have forces of attraction. So tight, right? And then I go to a liquid. So now they're still connected. I still have like that dot, 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 basically, when I show you on the slides. But now they're weaker and they're free to move. So a solid to the liquid, we are going to use the word weaken. Do not write the word break when you're talking about going from a solid to a liquid phase. It's weakening those bonds. When you go from a liquid to a gas phase, you are breaking those intermolecular forces. So be careful when you use your justifications that you're not saying something's breaking when it's not actually breaking. Breaking is that weak sort of liquid, and then all of a sudden the molecules go farther away from one another. And there are no attractive forces whatsoever in the gas phase. So we assume that there's no attractive forces. That's what we say the ideal gas law state, no attractive forces. So we're going to weaken when we go from a solid to liquid, and we're going to break when we go from a liquid to a gas. When we go from a liquid to a gas, potential energy increases. Why? They're moving far away. And in this case, too, they're starting to move further away from each other, but this is the greatest potential energy increase because it's going from a liquid to a gas phase. So just pay attention to the wording that you use on your free response. All right, next one we're going to use is dipole-induced dipole. So I gave you dipole-dipole. That is a polar covalent molecule with another polar covalent molecule. It could be the same one, or it could be a different one. This one is polar covalent and a non-polar covalent. So you'll see when we practice tomorrow, you're going to get, in this case, two different types of molecules. You can't have the same one because a polar molecule is not going to be nonpolar, right? In the previous example, when I said we have dipole-dipole, that could be with the exact same molecule, like water with water. But in this case, it's going to be two different things. So one of them is a polar molecule, and then the other one's a nonpolar molecule. So what happens in a nonpolar molecule is that you don't have, right, a pole of electrons. So, for example, when we had CH4. We know that there's polar bonds, but the overall molecule is nonpolar, right? Because it's symmetrical, the bond angles are all 109, it's all pulling in the same direction, pushing in the same direction, the electrons on both sides are canceling. So there is no dipole moment. However, you can induce a dipole moment because this polar molecule creates a positive end, right? So in other words, the electronegativity is pulling this way towards whatever this is, creating a positive end on this side. Because there's a positive end, what's in my nonpolar any molecule? What's in those bonds? Electrons. And electrons are what charge? Negative. So what happens is this electron and all the electrons in the bonds get a temporarily induced dipole moment where it pulls them over to this side, creating a polarizable molecule. So just for a minute, it's almost like a wave in the ocean. All of these electrons whoosh to one side for just a moment. And that positive end pulls all of them over, and then it releases them. So it's kind of like this little tug occasionally, and it tugs, and it tugs. But it's enough of a tug to pull on those electrons to create a temporarily induced dipole moment. So that's why they call it induced, because it's making it happen from another molecule, not on its own. Does that make sense? So it's nonpolar, but the electrons whoosh to one side, temporarily creating a negative end of that molecule, and then the other end becomes temporarily positive. And then it whooshes again. So anytime that you're inducing that dipole, you're pulling those electrons over. So this says the attractions result from dipole-induced dipole forces are stronger when the magnitude of the dipole in the polar molecule is larger. Well, why would that be true? So if I have a greater dipole moment in my dipole, my polar molecule, you create greater attractive forces because it's pulling those electrons temporarily much stronger, right? Always think of it like tug of war in this case. Like me pulling on you guys versus JC pulling on you guys, like he's going to have a greater pull and temporarily induce that dipole much stronger than I could. Pulling on all of you versus me pulling all on you, right? So the more polar the molecule is that is polar will temporarily induce a stronger dipole moment in the nonpolar molecule. So molecules that have larger dipoles have a greater ability of inducing a larger dipole in a nonpolar molecule. The strength of dipole-induced dipole forces also increases when the nonpolar molecule is larger and more polarizable. I'm going to talk about this in a little bit. But basically, the more electrons you have, right, in that previous slide, there was like one electron sitting out here. The more of those you have, that whoosh to one side creates more negatives on one side, right? So the more electrons that whoosh to one side create a stronger induced moment because there's more negative on one side, right? Like think of one electron going to one side versus 30 electrons going to one side. You're going to have a greater induced moment because those electrons are negative. All right, induced dipole. This is called London dispersion forces. They also sometimes are referred to as van der Waals forces, but we solely for this curriculum will use London dispersion. In SOT's class, they call them van der Waals forces. So the type is induced dipole, but we don't say that. We use this specific phrase, London dispersion. So I just want to, van der Waals is the other one that they call this. And then this is the main name that we're going to use, London dispersion. So what an induced dipole is, can you guess? What kind? Two nonpolar molecules. So nonpolar and nonpolar. And this is what I was talking about before with like dissolves like. A nonpolar species will dissolve a nonpolar species, right? So we are going to use London dispersion forces for everything. So I've been kind of hinting at where we're getting tomorrow. We're going to practice all of this together. So you kind of aren't sure how we're going to answer our questions. But one of the ways we're going to do it is I'm going to give you a bunch of molecules, and I'm going to ask you what types of forces of attraction are on them. Like, how does water stay in the liquid phase? It stays in liquid phase through hydrogen bonds and through London dispersion. So you're going to have to look at molecules, look at their structure, determine if they're polar or nonpolar, and then you're going to determine what kind of intermolecular forces they have on them. So London dispersion exists on everything. So make a note somewhere that if you're stating the intermolecular forces on a species, always include London dispersion. Always. There will always be London dispersion forces. That's a freebie. that is London dispersion forces exist on every single species, every single molecule. And I'll explain what it is in a moment. So even if it's a polar species, we're still going to call it London dispersion forces and then whatever else it has. There can be, though, molecules that only have London dispersion, and that would be just a nonpolar molecule. So London dispersion forces account for sometimes all of the attractive forces in a molecule to another molecule, and sometimes it's like a weak attractive force because like hydrogen bonding also exists. So hydrogen bonding, say, in water molecules would take up like 80% of the intermolecular forces of attraction, but London dispersion forces are like 20% of it. But in some molecules, it's the strongest force. So this is what happens. London dispersion forces is basically what I just described with a polar molecule inducing a dipole, except now you have just induced dipole through electrons moving from one side to the other side, from one side to the other side. So if the electrons go here, this side becomes negative and this side becomes positive, and another molecule's electrons move around, and we get negative and positive ends. So the forces exist between all species, atoms, ions, nonpolar molecules, and polar molecules, which I just told you. You put it on everything. They contribute to the overall force of attraction between all particles. They're the only intermolecular forces that keep assemblages of nonpolar species together. That just means the molecules, sticking these molecules together. Otherwise, if they had no polarity at all, they would only be in the gas phase ever, right? The only way that things come out of the gas phase is that they somehow stick together. And if they're not polar, then how do they stick together? They have to create some sort of positive and negative end to do that. So this is caused by the Coulombic interactions between temporarily induced dipoles of neighboring species that result from their electron distribution. So I'm going to show you a few more slides about this. In this moment, you have your nucleus in your center, and then you have electrons. In bonds, you have electrons in those valence shells. So instantaneous charge distributions are polar. So if those electrons go to one side of the molecule, you create a temporary dipole moment. At this moment, I've also created a dipole moment. And at this moment, I did. Are you watching the slides? Because that's not going to happen on yours. It's moving around, right? It's going back and forth. So at 0.1 seconds, at 0.2 seconds, at 0.3 seconds, at 0.4 seconds. So I have instantaneous polar moments, but overall, what happens to it? It's not polar, right? So like in CH4, which I drew up before, we have instantaneous polar moments, but overall the geometry cancels it out, so the molecule becomes nonpolar. But if I'm looking at electrons, electrons are whooshing around this molecule, and I can sort of grasp an electrostatic force of attraction between another molecule doing the same thing. So if this side becomes negative over here, then this side must be positive, and they'll align themselves so that they can have forces of attraction. So overall, the molecule is not polar, but you can get these instantaneous polar moments. So in an induced dipole moment, you can see that at 0.1 seconds, all of these will line themselves up with this minus, plus, minus, plus, minus, plus. At the next moment, it'll line up the other way, plus, minus, plus, minus, plus, minus. So it's kind of like this little pull, constant little pulls. So it's not a strong force of attraction at all, right? It's the weakest one that we have, but it accounts for how some molecules stay connected to one another and not just constantly in that gas phase. And all molecules have this because all molecules have, well, how do they all have London dispersion? How do they all create this instantaneous moment? Because they all have what? Electrons. And electrons are the things that are whooshing from side to side. So every single atom, molecule, ion has this occurring because they all have electrons, and electrons move. So we have whooshing from one side to the other side. So how do you know which ones cause the greatest London dispersion forces? Because we're going to be able to rank them. We can certainly determine, like the ranking we know so far, ions, the strongest, then ion dipole, then dipole, which hydrogen bonds are the strongest, dipole induced, and now we have induced dipole. So we know that boiling points change for all sorts of things, right? Not every boiling point's the same. So how do we determine which molecules have the highest boiling point and why? And it sometimes has to only be looking at if they are London dispersion forces. So if I'm only looking at London dispersion forces, the way that I determine this is based on the size But really size means how many electrons there are in the electron cloud, right? That's what size is. Energy levels are increasing. I think we have like 2 more minutes. Maybe not. Do you know time? Well, I'll finish the sentence.
No, this is the end, yeah.
So electrons are increasing, so my energy levels get larger. The more electrons you have, the more polarizable, meaning that induced moment is, the stronger it is. So more electrons, how do you count them? You literally look at the periodic table, and you say for chlorine, you go and look how many electrons it has. It has 17. Cl2 diatomic, 34 electrons. Same thing that you would do here. You literally count how many electrons there are in the molecule. Okay?
The more electrons, the stronger the what?
Polarizability. All right, so we'll pick up tomorrow. Okay, so we left off with this graph yesterday about boiling point, and it does say molar mass, but really what we're looking at is what? The number of electrons that are in there. So larger species with more electrons are more polarizable. So you get that whooshing to one side and the other with so many more electrons attached into that molecule that push to one side. So if you have 120 electrons in a molecule and 120 of them are whooshing over to one side versus 8, that's not that many, right? Like CH4 has 8 electrons. 10, just joking, 10 electrons. CH4 is 6 for carbon, and then each hydrogen has 1 and there's 4 of them. So CH4 would have 10 electrons versus something else that could have over 200 electrons. So the more electrons there are, the more polarizable it is. So you get that whooshing, induced dipole moment much more heavily. So as you go up, you can see you start with helium, and then F2, how many electrons does this have?
9.
14.
Oh my word.
18.
18. Not balanced. All the electrons in the atom are whooshing. All of them. They go to one side. So we have 18, chlorine, Cl2. Get it? So you're just adding them up, literally looking at the molecule and adding them up. All right, this next slide. Go ahead and read that. So they have a weaker hold on their outer electrons. When moving down a group or constructing molecules with more atoms, the resulting species has more electrons and is larger. The more electrons a species has, the more polarizable it is. This is not always the case when moving from left to right across a period as atomic radius decreases. What happens when atomic radius decreases?
It has a stronger pull on one.
Right, so that whooshing might not be as pushed because the nucleus can hold on to its valence electrons or any of those electrons a little bit more tightly. But as you get larger and larger, it's harder to hold on to those electrons. We know this from Coulombs Law. And so you can have a push of those electrons to one side. So don't just write the words larger, like the molecule's larger, therefore it's more polarizable. I want you to make sure that you include there are more electrons, therefore it's more polarizable. All right, pi bonds, shape and polarizability. All of this, when you look at molecules, you really are checking first if it's ionic or covalent, and then you're checking to see if it's polar covalent or non-polar covalent. You do that by geometry. So last test, some of you still struggled with whether or not things were polar. You need to think of it like a car. Is your car moving? Is it going to move in one direction, or do all of the pushing and pulling, does it cancel out? So you'll also be able to determine this from geometry too, and we'll get to that, I think, in lecture 2. But first thing is pi bonds. What are pi bonds?
The next bond.
Okay, so like the second or third bond, but it's the what kind of p orbital? Unmorphed p orbital. So if I have an unmorphed p orbital, I really have like this going on where electrons can be delocalized, right? So more delocalization means more whooshing, right? Like a wave. Like you can push off to this side versus that side. If you have hybridized, you end up with those head-to-head interactions and you don't have much ability to move as much. So electrons and pi bonds have more freedom to move, therefore pi bonding has more polarizability. An overall geometry that allows neighboring molecules to approach one another more closely will facilitate the formation of more and stronger induced dipoles. So here's 2 different structures. These are called isomers. What is an isomer?
Like they have like the same something but different something. Good.
Someone fill in those words. The same something but a different something.
Different.
Same.
What's the first letter? Proton.
Same number of.
Rhymes with, no. It's the same chemical formula.
Yeah.
Like you have all the same carbons and all the same hydrogens, same number of carbons and hydrogens.
Different number of.
Different geometry, different arrangement. So the structural formula is different than the chemical the chemical formula is the same for both of them, but the structural formula is different. In other words, the arrangement of the atoms is different. And that's obvious in this case, right? You can see that?
See.
So intermolecular forces are this thing going on, right? So if I line up nicely and I can make intermolecular forces, then I have stronger forces of attraction. Versus like I'm trying to line up like this, I don't have great forces of attraction. It's like these are hangers. Think of it as hangers. So I'm packing a box, and I pack my hangers in nicely, and I pack them all in. Gonzo, he cleans up his hangers in his room, and he just picks them up and dumps them in the box. Right? Really messy. That's what this looks like. They're not stacked nicely. So which box is going to have more hangers in it? My box, right? And which ones are going to have stronger forces of attraction? The ones that are touching each other more are going to have stronger forces of attraction, right? So these can stack nicely, stronger forces of attraction. Those don't stack nicely, weaker forces of attraction, even though they have the same number of electrons. All right, this is a great list. It's not comprehensive because I'm going to teach you about solids, and solids have something called Covalent Network solid forces of attraction. So Covalent Network solids are the top. You just don't know them yet. I'm going to teach them to you in the solids lecture. So something like diamond, that is really strong. You should know that, right? Diamonds are really strong. Silicon dioxide, glass, that's really, really strong, right? Like in order to get glass to melt, you know that you have to apply really high temperatures to that. So the first type is covalent network solids. You're literally just going to memorize a list of them, and then you'll just know when you see them, oh, this is a covalent network solid, so it must be the strongest type. Beneath that is ion-ion. Everyone misses ion-ion. So like on your test, I'm going to give you examples, and you're going to have to rank them. And I'll tell you the one question that everyone typically gets wrong, like the majority, will be that you don't recognize ion-ion. You try to make it a covalent bond. What is ion-ion? A metal with a nonmetal. So if I give you NaCl or MgOH2 or anything, iron chloride, iron trichloride, you have to first ask yourself, is this an ionic compound or is it a covalent compound? And if it's ionic, it's going to be stronger than any of these other forces because these are like intermolecular forces where ion-ion is electrostatic between a cation and an anion, right? That already has positive and negative. You don't have to induce a positive or negative. It already does. So ion-ion is for ionic compounds. Ion dipole. This is when you have an ionic compound with a polar molecule, polar covalent. So that was what we discussed when we said sodium chloride dissolves in water. Or any ionic compound can dissolve in a polar molecule. Hydrogen bonds here is what starts our covalent bonds. So once you look at what type of compound you have, you can determine if it's ionic or covalent. Then once you determine if it's covalent, then you start examining what type of covalent bonds you have. So the first type, the strongest type, would be hydrogen bonds. And we know that that's hydrogen attached to an oxygen, nitrogen, or fluorine, and then also attracted to the lone pair electrons on an oxygen, nitrogen, or fluorine. Then beneath that are your dipole-dipoles. Those are any polar molecules. So polar, covalent, and polar covalent. So it can be two different types of polar covalence, or it can be the same molecule just in a pot of other molecules like it. Ion-induced dipole is an ionic compound plus a non-polar covalent. This is not really that strong because this is only going to be able to induce a dipole on something else, right? So this doesn't have a negative end, positive end on its own. It's just creating one because the ionic portion can pull the electrons. Dipole-induced dipole is a polar covalent plus a non-polar covalent. Let me give you an example of this one. A polar covalent molecule and a non-polar covalent have to obviously be two different types of molecules. So, for example, I have water, Definitely polar, it has H bonds, right? And then I have carbon dioxide. What is this? Nonpolar, right? Well, we know that carbon dioxide dissolves in water. How do you know that? Like soda? Like you all drink soda, and carbon dioxide is dissolved in there. Well, according to intermolecular forces, that doesn't make so much sense because this isn't polar and this is. So how do they attract to one another? How do you get, this is a gas. How do you get a gas to dissolve into a liquid? Because it does, and you know that, right? So what? Nah, it'll happen no matter what. Actually, you do it based on pressure. When you make your soda, if anybody has one of those soda streams at home, you have to pressurize it. But carbon dioxide will naturally dissolve in water. Oxygen naturally dissolves in water. How do you know that oxygen gas naturally dissolves in water? You know this to be true. There are those little things that fish swim, and what do they breathe? Oxygen, because it's dissolved in the water. So how do you get any nonpolar substance to dissolve in a polar substance is through polar covalent and nonpolar covalent, which is a dipole-induced dipole. So when you have a water molecule, you line up your end, you have a negative end and a positive end to this, right? We can orient oxygen like this, and this becomes slightly negative. Well, when you put a nonpolar substance, you know that you can temporarily induce a dipole because all of the electrons in here will, for a moment, whoosh to one side and be attracted to the positive end over here, right? So I temporarily induce that dipole moment, and it's just a little tug, like a little tug on that carbon dioxide that pulls it towards it and keeps it dissolved into your water. And I'll talk more about like carbon dioxide and how, because you know that eventually the carbon dioxide goes away, right? What is that called when your soda goes flat? And so I'll talk about that in the gas laws section. But for right now, you just have to know how they mix, and they mix through dipole-induced dipole forces. And then the last one, the London dispersion, is on everything. We talked about that already. This is nonpolar covalent and nonpolar covalent, but it also exists on everything. I say nonpolar because if you have only nonpolar substances, then the only thing we can say is London dispersion forces. But this exists on all. And that's because everything has electrons, don't they? So then it exists on everything. Good? All right, so now we're going to practice. All right, we're going to do a few slides. This one we'll do together. All of your homework questions and the free response questions that you're going to get are usually asking you which one has a higher boiling point, which has a higher melting point, or why does this substance dissolve in this substance and this other substance doesn't dissolve in it. So remember when things dissolve in each other, we use that phrase like likes like, or like dissolves like. So polar substances will dissolve polar molecules because, say, their dipole-dipoles can interact more than a dipole-induced dipole, right? Dipole-dipole is stronger than dipole-induced dipole, so we would have stronger forces of attraction there. So all of your questions are going to ask you, like, what happens with this, or which one has the higher boiling point? And you always have to compare and contrast and talk about both molecules. So you can't just pick one and say this one because it has hydrogen bonds. You have to talk about the forces of attraction on each of them. So C2H6 or C3He? So if you're not sure of structure, draw it. All right. Both substances are nonpolar, agreed? Yeah. In other words, the car doesn't move. The carbons aren't moving anywhere because the pull of electrons is the same throughout the entire structure. It cancels, right? So both are nonpolar. So what are the forces acting on this? C2H6. Only London dispersion forces. And on this one, only London dispersion forces. So that's what you're going to do. You're going to talk about the polarity of each molecule. You're going to talk about the forces that exist on each of those. And then you're going to state which one has the higher boiling point due to the stronger intermolecular forces. Well, these are both the same forces. So now how do you pick? Electrons, polarizability. This one has more electrons, therefore it's more polarizable, so the boiling point will be higher. So that's how your justification will work. So there was some question in the other class. They were like, well, am I mixing these two? No, it's like a big pot of Avogadro's numbers worth of each of those molecules sitting there interacting with one another. So whoever is stronger with each other is going to have the higher boiling point. So more polarizable, therefore, it has a higher boiling point. So I would avoid using the word the larger molecule. You can say that, but just make sure you say that it has more electrons. More electrons makes it more polarizable. All right, let's look at the next slide. You guys are going to try these on your own. So which species has a higher boiling point? In this spot here, I want you to tell me if it's polar or nonpolar. In this spot here, I want to know what types of forces are here. So intermolecular forces is IMF. So I want to know what kind of intermolecular forces. And then I want you to write low or high for the boiling point. Okay? Try it out. So first row, we have polar or nonpolar for the first molecule? Polar. Polar. And then C3H8, nonpolar, right? So if you're not sure, this is what you're evaluating. 1, 2, 3, you know what all those are, hydrogens. This has no polar push in any one direction. Your car doesn't move. Do you know what I mean by car? Yeah. Like if you're all pushing on those carbons, they're all equal force around it, so they're not going to move. This has an OH. So the pole of electrons is headed towards this oxygen. So this end is going to become slightly positive, and this end is slightly negative. Agreed? Oxygen's more electronegative. So then what are the forces acting on the first one? Okay, London dispersion, yes. Nobody else came up with the right answer?
H-bonds?
Thank you, Gonzo!
Really?
Yeah.
Yeah, I told you guys.
No, so this is what you have. Perhaps you're confused. When you look at this molecule is sitting in a pot with Avogadro's numbers worth of other molecules like it. So if I put in another molecule like it, here it is, hydrogen bonds, and then like a million other hydrogen bonds, right? When water is sitting in your bottles right now, water is connected to each other because all other water molecules have hydrogen bonds, right? So this is hydrogen bonding available. So the way you'll recognize hydrogen bonding is that you're going to see hydrogen attached to an oxygen, nitrogen, or fluorine, and if it's the same substance that it's hydrogen bonding with, clearly there's going to be a lone pair of electrons on it. So hydrogen bonds and London dispersion. If you write dipole, it's wrong, because even though this is a dipole attraction, it's a specific one called hydrogen bonds. And then this one, only London dispersion because it's nonpolar. So who has the highest melting point? First or second?
First.
So boiling point 78 degrees C, boiling point's negative 42. Good? That first structure there is ethanol. The second structure here is propane, like in your propane tank, right? Your gas grill. This is alcohol that people drink, ethanol.
People drink it? Oh, like, I'm thinking like ethanol. What am I thinking? Like gasoline. Yep, that's why it's ethanol gasoline. No, it's alcohol. No. What's gasoline?
There's different types of gas, like propane, that kind of stuff. Propanol, methanol, ethanol, all that.
Methanol.
Okay, next one. But they have different amounts.
Wait, which one had the low and high?
I was like gasoline.
All right, next one. Same thing. Polar or nonpolar? What is your type of intermolecular force? Low or high? This one is like meant to just ask you to kind of justify a little bit more, but you can leave that line blank because you're not sure what to do with it.
So there's. You didn't get my big aha moment. Do it again.
2 hydrogen bonds. All right, so hydrogen bonds in my list of all of the forces of attraction, hydrogen bonds trump London dispersion, don't they? But you guys who said you're right, this one does have more electrons, so it is more polarizable. So now you just have like a double whammy here. Like definitely more hydrogen bonds is going to make this boiling point much higher, but you kind of had this like other thing on the side, London dispersion, being more polarizable. What if this one was bigger, but this one still had 2 hydrogen bonds? This would still trump it, because hydrogen bonds are so much stronger than London dispersion forces. So we end up with the right one being a much higher boiling point with 188 degrees. Make sense? All right, the next one. So which has a higher melting point? Oh my goodness, I changed the word on you.
No.
Does it matter?
Yes.
No, but in your justifications, what words are you going to use differently? Okay, but weakening versus breaking, right? So this is a weakening of the intermolecular forces. So tell me if it's polar or non-polar. Tell me the forces of attraction. Give me some sort of justification here in the 4th line, and then tell me which one has a lower or higher boiling point, melting point. Okay. So we have CH4 and CI4. Polar, non-polar. Which ones?
Both not.
They're both non-polar. That's right, because the geometry cancels. Agreed?
Yes.
All right. The next one. What are the intermolecular forces?
LDS.
Only London dispersion on both of them. So now, what are you gonna do?
Electron count.
Electron count. How many electrons are in CH4?
10.
And how many are in CI4?
218.
Good boy.
Whoa.
Yeah. So, larger, more electrons makes it more polarizable. The melting point for this is 171 degrees Celsius. This one's negative 183.
Can I say my justification for why it's high?
Okay.
Oh, really?
Yeah.
Alright, so more electrons makes it more polarizable than fries and iron.
Yeah, so if that was your justification, you would lose some points. So you were just going to practice them today, but let me give you the proper justification. And now, I don't think the AP exam tells you to do this anymore, but they used to say, make sure you include the intermolecular forces on each species. They would say that to you because they know students would just skip and go straight to the answer. So the first thing you have to say, the reason why I'm making you make this chart is because all of this needs to be in your justification in paragraph form. So you would say, both species are nonpolar and have only London dispersion forces acting on them, right? In the other example, we would say, this species is polar, has London dispersion and H bonds. This species is nonpolar, only has London dispersion. So you describe both of them first. Then you will say, CI4 has a higher melting point because it has more electrons and is more polarizable. Therefore, it takes more energy to weaken these intermolecular forces of attraction. That's it. So you got to talk about both of them. Yes?
If we're comparing the CI4 to like that CH3OH in the 3rd example, because that one has a hydrogen bond and like...
Hydrogen bonds trump everything.
Okay, so that
Yep.
one goes before hydrogen bond.
Was this the last slide?
No, more.
Oh.
Oh, my bad.
All right, sodium chloride and water.
What's that? Oh. NaCl.
All right, first one, sodium chloride. So we can't write what?
Polar?
Why can't we write polar? Because it's ionic, right? So polar only refers to when a molecule creates its own slightly negative and its own slightly positive end. Remember that molecules are entities, right? They're these species, whereas a cation anion is just a solid network of all of these pluses and minuses attracted to one another. So this has no polarity to it. So it is simply ionic. And this one is what?
Polar.
Polar, right? So right away from our list, we should know which one should be stronger.
H2O.
Oh my goodness. So this is where I would hope that common sense would play a little role. Like you're thinking about which one has the highest boiling point. I would hope that you would realize that a pot of water is going to boil before all of that sodium chloride on your stove. Like take a pot and pour salt in there and then turn the heat on, and which one's going to boil
I
off?
wasn't thinking like that.
I know. Yeah.
Yo, can we do it for
Yes.
No.
So look,
No.
hydrogen bonds,
No, man.
London dispersion. But you would have chose incorrectly if you didn't recognize ionic right away. You have to recognize ionic. So before you look at anything else, Always ask yourself, and you'll get to this part too, where you'll say, is this a covalent network solid, or is it ionic? And if it's not, then you go straight to all of your covalent stuff. So because it's ionic, that's much stronger force of attraction. It's actually positive and negative cations. Look at that boiling point.
What?
Just a little bit higher. I could see if you got confused. All right, so now take out your worksheet.